Yeah, I have a small joke that I wish to share with you. I mean, it's an incident that happened that I can never forget actually. And it is motivating me to do something else. Okay. Yeah, so I had a fever in the month of April, in the mid of April. I was taking rest actually. In the afternoon, I got a call. Okay, I usually get a call from many marketing executives. I mean, startups who does marketing, digital marketing. Okay, so because they see my what you call Facebook poster, they see my web page like that. They see what are the coaching classes in Dharwad. They search and they contact individually, and they say we are going to do digital marketing on behalf of you. Like that they say. Okay. So it was fourth or fifth call that I got from last one year. Okay. So so my phone was ringing. I just picked up the call and I said hello. On that side, one lady, she was saying we are digital marketing experts. So we wish to offer you a service. Am I speaking to SN Bose? She asked like that. You can enable your mic and laugh. Okay. She asked, so am I speaking to SN Bose? I had a fever. Okay. I was sleeping and I woke up and picked up a call. And she asked me, am I speaking to SN Bose? Then I was very angry and I told her, you know who is SN Bose? She thought, she said, I think SN Bose might be the owner of this coaching class.
Owner of this coaching class?
Yeah. So she thought like it is a Bansal coaching class.
So he became SN
Byju's, like that. I mean, yeah, I was so angry that I mean.
Oh, sorry, you should be happy. She know that he will be SN Bose.
No, it is sad also, isn't it? Again, in one side it's a joke, in other side it's very sad. In other side it is very sad, isn't it? Again, they don't know about
SN Bose.
one of the scientists of our country, isn't it? And they do something, isn't it? They do marketing. That's not what you call. Yeah. I couldn't actually. I was so angry because I used to be angry when such a call comes actually. Okay, what my belief is, people should work on product, not on marketing. Okay.
Again, sir, mic is muted.
I think this might be some other driver problem. Anyway, I'm switching over to some other. Yeah, you quickly tell me, okay, when mic is muted.
Voice suddenly.
Yes. No, that also might be some issue with Windows only. Okay. Yes. We were discussing anyway. Again, and one more thing is that's okay. She might not be from science background. So many students called me for enrolling for this class. So they call and they ask, is this JC Bose coaching center? They don't know difference between JC Bose and SN Bose. I mean, JC Bose also did many experiments related to physics, but once they read SN Bose, they should know who is SN Bose, who is JC Bose, isn't it? They don't know that difference. I mean, who are masters in physics actually. And obviously, you can expect those kind of calls, isn't it? From people who are other than science background, obviously. Yeah, so that's why Elon Musk always says that again, you should work on product, not on marketing, isn't it? If you work only on marketing, this will happen. You will never know about that product. Is that okay? Yes. Yeah. Now so I'll quickly continue with one more part. Compton effect. Yeah. So in case of Compton effect, I will give you one suggested reading. Okay. If you are free, then only go through that one. Okay. So that is, at what wavelength Compton effect happens, at what wavelength photoelectric effect happens. Okay. This is highly studied in nuclear physics. You better to go through atomic nucleus. By R.D. Evans. Okay, very nice textbook, very logical explanation. Okay, in that one, I think around page number 700, 600, there is one chapter on that one. Okay, they study Compton scattering cross section, photoelectric effect cross section like that, pair production cross section like that. Okay, so pair production will not happen again. We shall study now. So pair production will not happen at very low energy photon. So again, in the region of UV visible, your photoelectric effect dominates actually. That probability is more. In the region of what you call X-rays, Compton effect is more probable. I think he might have given some more logic behind that one. I'll try to grab that one. Okay, a whole chapter should be read. If you are studying any electronic or something, yeah. No. Best again book. The best book for nuclear physics is Crane actually. But this is also very old textbook and contains lot of logical explanation. RD ones. So in that one, it is studied well. Okay. So if you have time, then only go through that one. Okay. Not much required for our exam, because again question comes, isn't it? Why not what you call your photoelectric effect happens when in case of X-rays, isn't it? Are you getting my point? So that kind of question comes actually. So again, those are probabilistic events. Those are probabilistic event again that you need to run, and I'll try to what you call give you much more idea if I got any idea from that one. Okay. Yeah. Again, in case of Crane book, you may see that advanced math is there. Not advanced math. Okay, it's all quantum mechanics actually. So he gave that quantum mechanics in the beginning of the textbook. Anyway, we shall deal with that one later. Okay. So now one more, again, Compton effect almost convinced us that light composed of photon. Okay. So now we have one more event, that is pair production. So pair production. So which also what you call so convince us that light composed of photons like that. Okay. So now look at here. So it again, so after this this particle nature of light, and after this de Broglie hypothesis, quantum mechanics started by Schrodinger, Heisenberg and all. Okay. So, but whatever the quantum mechanics that is developed by Schrodinger and Heisenberg, those were non-relativistic. Whatever Schrodinger equation you see, whatever the Heisenberg mechanics you see, those are non-relativistic mechanics. Those cannot be applied for relativistic case. Is that okay? So later, I think in 1928, Dirac proposed one idea. Again, so Schrodinger himself gave some idea regarding relativistic Schrodinger equation. We call it as Klein-Gordon equation, but it has some loopholes actually. Okay, Klein-Gordon equation have got some loopholes. Let me try to so try your attention to that one. Anyway, we are going to study that one at the end of the quantum mechanics. Okay, so now look at here. In relativity, you can derive this one. E square is equal to P square C square plus ME square C power 4. Okay, P square C square plus ME square C power 4. So if my volume is muted, you quickly tell me. Okay, yeah, can you hear me? Can you hear me? Yeah, okay. Now in relativity, in special theory of relativity, we can directly get into this equation, not E. Okay, E square. Okay, so now from this equation, if you want to write E, what would you do? So this is for free particle. Free particle, relativistic case. Free particle. Is that okay? Not any bound particle. I am not taking any force here. Okay. So E, what would you write? E equal to root of P square C square plus M naught. I will not write M E. I will write M naught. Okay. Any particle. Okay. M naught square C power 4. Okay. Now look at here. Here is the mistake that we do, isn't it? Each and every mathematical thing have got physical meaning. So this pair production and the theory behind that one, that will convince us actually. If suppose if you have x square is equal to 4, okay, what is mathematically x can equal to plus or minus 2, isn't it? Plus or minus 2, isn't it? Are you getting my point? But what we say, look at here, it's a free particle. How free particle can have negative energy, isn't it? So again, even though mathematics says plus or minus root of this one, okay, but what we say, look at here, it's a free particle. How it can have negative energy? Maybe mathematics, again, maybe all mathematical part may not have physical significance. That's what we think, isn't it? Are you getting my point? And again, in case of even Compton effect also. We have taken the same thing, am I right? We have taken positive root, isn't it? We have taken this equation. So, but again, at the end of quantum mechanics, when they developed relativistic quantum mechanics, so Klein-Gordon equation by Schrodinger himself, okay, they tried to explain this one actually. So they tried to explain this one, but in case of Schrodinger relativistic equation, Klein-Gordon equation, okay, so there was some problem, okay. If you take negative root of this one, you would end up with negative probability. I hope you know that something, mod square of wave function is the probability density, isn't it? Suppose if you take negative root of this energy, okay, if you substitute and if you take mod psi square, you would end up with negative probability. How can you explain negative probability, isn't it? It is quite meaningless. Even Schrodinger himself tried to fix that one. He multiplied that one with charge and he tried to say it is a probability charge density so that we can interpret that one. But that's a kind of fix, not complete explanation. Is that okay? So that's why Schrodinger relativistic equation was not accepted very well. Okay. So then comes Dirac in 1928. He edited Hamiltonian. He gave his own Hamiltonian. Okay. Usually how do you write Hamiltonian? Or so total energy P square by 2m plus V, isn't it? Again, in case of quantum mechanics, we write operator. You will learn that one later, okay? But Dirac edited this whole Hamiltonian. This is non-relativistic one, okay? So again, so Klein-Gordon equation also contains similar part. But what Dirac did was, Dirac edited Hamiltonian. So anybody remember alpha dot P plus beta m naught C square. I think C is multiplied. He edited Hamiltonian. This is for free particle, okay? No potential is included. P vector means it again contains operator. Anyway, we shall deal with this one. This is also operator actually. So that Dirac Hamiltonian, what you call, look at here, our spin concept came first actually. Spin concept first, so it came first in this kind of in this Dirac relativistic equation actually. So again, that equation, again, if you talk about probability or something, again using that equation, there was no problem if you take negative root here. In the Dirac Hamiltonian, in the Dirac approach of relativistic quantum mechanics, even if you take negative root, you had no problem. No inconsistency, no ambiguity over there. So then obviously you can accept that one. And again, lot of research still it is going on using Dirac Hamiltonian, so in condensed matter and all, in case of relativistic case. Okay. So now look at here. That's why negative root also have meaning. Remember, also have physical significance. Are you getting my point? Negative root also have got significance. Now it is quite disturbing. Remember, it is quite disturbing how free particle can have negative energy. We can't imagine that one, isn't it? It's a free particle. How it can have negative energy? But mathematics instruct us that possible energy can be negative also, isn't it? And one thing you need to observe in case of free particle, okay? Now look at here that this Dirac theory, it can be applicable only for Dirac particle, I mean spin half particle or half integer spin particle. Is that okay? This Dirac Hamiltonian and Dirac theory, that can be applied only for fermions. Yeah. So or we say Dirac particle simply, okay? Now look at here. So one thing that you have to understand here, this E, okay, either positive or negative, this should be greater than m naught C square, okay, when it is positive, isn't it? Obviously. So if it is equal to m naught C square, it is at rest. We say rest mass energy, am I right? So or it is less than minus m naught C square, isn't it? So can you see this one? Yeah. So quickly, any question?
Practically negative with an energy possible.
Wait a second. I'll complete that one. Practically, yeah, again, our practical things are because of our common sense, isn't it?
Who says quantum mechanics practical?
No. But the beginning parts you may feel impractical, but once you see application, you will start believing that one. Are you getting my point? Wait for a while. Is that okay? So now, E is greater than m naught C square. Either, again, if it is positive energy, again, I'm going to call it as positive energy states. Is that okay? I hope you know something about state. Suppose in case of hydrogen atom, ground state, first excited state. So Bohr orbit, we say So states, isn't it, like that, okay? So, but this is continuous energy state, okay? This is not discrete, is that okay? There is no discreteness here. So E is greater than m naught c square. If it has positive energy, it should be less than so minus m naught c square. Let me write greater than or equal to also, okay? Anyway, quantum mechanics will not allow particle to be at rest actually. Anyway, so a lot of questions may come here, but look at here. If you try to draw this one, okay, this is energy. This is energy, okay? So this is 0. This axis is nothing, okay? This axis is nothing. This is energy, this is 0 energy. It's a kind of band diagram in case of semiconductor. I hope you know that one, okay? So now you have to mark plus m naught c square here, okay? Minus m naught c square here, okay? So now look at here. So you have a states here, possible states of the free Dirac particle. Let me take free electron, okay? Because he was addressing electron over there. You have states here, possible states here. So since there is no discreteness in the state, I have drawn like this. Is that okay? You have possible states here. This is forbidden, okay? So this is forbidden. So this equation says you can't have any energy state in between this one. Is that okay? I hope you can grab that idea. So there are continuous energy state in this one and there are continuous energy state in this one. And look at here, free particle, let me take electron, okay? For example, so let me take electron, okay? Electron, it can be in the positive energy state, free electron. It can be in the positive energy state also. Free electron can be in the negative energy state also, possibility. Okay, in the Dirac there is no ambiguity for this one, okay? So it has some physical significance. So that's why, again, electron can be in the negative energy state also.
Sir, you are saying cathedral or equivalent or what?
No, I actually, again, so if it is there, it is at rest, am I right? It has only rest mass energy. It is at rest, isn't it? To avoid that one, I better to write like this. If it is at rest, again, you will ask about uncertainty principle. Isn't it? Yeah. So wait a second. So what I am saying is, again, these are continuous energy level. Electron, free electron that can have positive, that can be in the positive energy, just like, look at here, in case of hydrogen atom, minus 13.6. So minus 13.6 divided by 4, like that. You have different states, isn't it? Electron can be in this state, electron can be in this state, possible states, isn't it? So according to our Bohr theory, now we haven't showed in the equation yet, okay? Now, say similarly, electron, free electron can be in this state, somewhere in this state, or free electron can be in this state. Now the question that he asked, isn't it? Is that practically possible to have, for a free electron to have negative energy? Isn't it? That question comes, isn't it? Now, the idea is, it looks like fixing thing, okay? But this is the nature because we have experimental proof for this thing, okay? So, if electron is in the negative state, what you call energy state, electron can be in the negative energy state, but it will have no physical appearance. Are you getting my point? It will have no physical appearance. If electron is in the negative energy state, it will have no physical appearance. Whatever the electron we see, those are in the positive energy state, somewhere here. Suppose if you take your cathode ray or any atom or something, okay? So those are in the positive energy state. Electrons in the negative energy state, they have no physical appearance. Now the question comes, where are they, isn't it? If they don't have physical appearance, how do you find where are they?
Yeah, that's what
Yes. So quickly. Yeah. So question. So that was a question, isn't it? If they have no, once I say that, they have no physical appearance, isn't it? How do you say where it is? If I say it is there, then it should have physical appearance, isn't it? It has no physical appearance, you can't find where it is.
So what's the probability behind it?
No, wait a second, it's not complete. The idea is not complete. Is that okay? Now the question comes, okay, you have one free electron in an atom or suppose in a metal or in case of cathode ray or something, okay? You know about spontaneous emission? I told you, isn't it, about Einstein was a legend, isn't it? I mean, he might have done some mistake in case of Bose, but he is a legend, okay? That stimulated spontaneous emission, no, stimulated emission, okay? That lead to separate field, laser field, remember, okay? The Einstein's each and every idea give rise to one path actually. Yeah. So anyway, spontaneous emission. Okay, you know how spontaneous emission happens? Atom in the excited state, how it comes back to ground state? What is the motivation? Again, that answer lies in field theory again. Is that okay? Even in vacuum, even there are no photons, you will have some what you call fluctuation of electric field and magnetic field. We call that one as vacuum fluctuation. I'm going to argue that one in the harmonic oscillator model. Okay. So in case of quantum harmonic oscillator, I'm going to argue the same model is applied for electromagnetic fields. Okay. So again, even in vacuum, you will have some what you call fluctuation of electric field and magnetic field that causes actually spontaneous emission actually. Is that okay? It don't need any photon. Again, it's quite hard to believe. Again, I'll first propose the whole thing, then I'll try to convince that one. Right now, you may have much more questions. Okay, so just hold on that one. Now, again, if any electron is there here, which we can see this electron. We can do experiment with this one. Now look at here. Again, by making some spontaneous emission, it can go to this negative energy state, isn't it? And that spontaneous emission, again, so that is easily triggered. That is easily triggered. I get my point. Electron will not be there for a long time here. So it will go to negative energy state by emitting, look at here, photon of energy greater than m0 c square. What is m0 c square value for electron? It's around 1 kilo electron volt or mega electron volt? 1 mega electron volt. So greater than 2 m0 c square. This is 2 m0 c square. Sorry, is that okay? So if it make the transition from here to here, any possible state here, then it will emit the photon of energy, very high energy. So greater than 2 m0 c square. Is that okay? And this is what you call all again. This is easily triggered. This is a spontaneous emission. You don't have to do anything. Okay, suppose if you excite any atom in the hydrogen atom, okay, so if you excite electron in the hydrogen atom, it will spontaneously come down. It will not live there for a long time. It may live there for microsecond, millisecond or nanosecond like that. Is that we call that as lifetime of the states and all. Is that okay? Like that, if there are allowed state here, okay, if there are allowed state of less energy, it will definitely do some spontaneous emission. And it will go down to that state. So this leads to one problem that, look at here, no electron in nature are stable, isn't it? All electrons should go to the negative state by emitting what you call gamma photon. So again, this is in the gamma ray region, okay? And none of the electron in the nature should be stable, isn't it? If this happens, okay? If this happens, none of the electron in the universe would be stable, and universe would not exist, isn't it? If atom doesn't exist, universe will not exist, isn't it? Are you getting my point? Now, what makes this electron stable, isn't it? Free electron, which has a physical appearance. Free electron, which is in the positive energy. What makes it what you call stable, isn't it? Why it is not making the transition, spontaneous emission, a spontaneous what you call transition, isn't it? So now again Dirac proposed the idea that there exist negative states, okay? There exist negative states for free particle, but all of those negative states are filled, completely filled by what? Electrons only. Suppose if you take one negative energy state, that negative energy state is filled out by 2 electrons, because again I hope you know about Pauli's exclusion principle, and again and spin concept, isn't it? Electron is spin half particle. Each level can be filled out with 2 electrons, isn't it? Suppose 1s, you can put 2 electrons here, isn't it? So 2px, 2py, 2pz, isn't it? So there are 3 p orbits actually, 3 orbit orientation. That's what we say, am I right? So 2 here, so total 6, isn't it? Like that. Each state can contain 2 electrons. One is spin up, other is spin down. I hope you know this one, this kind of scheme, isn't it? So now, there exist negative energy states, but the whole negative energy state, it is filled, completely filled. Okay, I'm going to draw it like this symbolically. Okay, each negative energy states are completely filled. So now look at here. In case of hydrogen atom, okay, if K shell is completely filled, okay, so higher orbit electron will not go, again in case of atom, not hydrogen atom, okay, in case of atom, if K shell is completely filled, so again higher orbit electron will not come to K shell, isn't it? Completely filled means if one more electron comes, Pauli's exclusion principle will be violated, isn't it? So like that, there exist negative energy states, okay, but they are completely filled with electrons. So that leads to the stability for this electron. Again, if they make the transition, so then in one state there will be 3 electrons. That cannot happen. Electron is spin off. You can put only 2 electrons in each state. Are you getting my point? So once it is completely filled, so there will be no more electron. So that can be possible in any of these states. Okay, because it will violate Pauli's exclusion principle. Is that okay? So that this one, so since those negative energy states are completely filled, that's why our positive energy state electron in our atom, in our metal, everything, they are stable. For God's sake, universe exists, isn't it? This argument is true for Dirac particle. Okay, this whole theory is true for Dirac particle. If you go for bosons, you should go for some other theory. I think you better read R. Shankar. Okay, I mean Feynman theory. So some different theories there for boson. Still, I have some what you call logical question in that one. Why different theory for those things? Since these equations are same for both, but why different story? Again, we shall not get into that deep. Okay. For bosons, I think Feynman gave the theory. You can just read out that one. Okay. Now look at here. Now look at here. The reverse can happen. Am I right? If electron is there here, it can absorb energy. Why can't it goes to what you call positive energy state? Isn't it? That can happen. Isn't it? So just forget you have a space. Okay. So you don't have any electron. But again, you have negative energy state. You have completely filled. So negative energy state by electron. Now suppose if you incident a photon of energy h nu, which is greater than this band gap, greater than 2 m naught c square, okay, so that energy can be absorbed by this electron, and again that electron can go to positive energy state, isn't it? If electron from here, if it goes to positive energy state, yeah, we call that one as electron only, okay, but here comes a vacancy. So can you feel that one? Here comes a vacancy. So again, this transition will not happen from above to below. Transition will not happen. Okay, that's what I said, because these are completely filled. But here you have electron, am I right? They can absorb energy which is greater than 2 m naught c square, and they can go to positive energy state. Once it goes to positive energy state, this electron have got physical appearance. Positive energy state electron have got physical appearance. Now, once it goes here, it leaves behind vacancy, isn't it?
Sir, how can it go? Because this energy is less than m naught c square.
No. This is the energy state of the particle. I am saying I am going to incident a gamma ray photon. Okay. Electron from here, which absorbs energy greater than 2 m naught c square, it can go to that state, isn't it? Yes. Absorption. We say absorption in case of atom. Isn't it? That can happen. It's a possibility that can happen. Now again, if it does, look at here it creates one vacancy. Remember that vacancy is very similar to your hole in case of condensed matter physics. So in case of your semiconductor, is that okay? Now this hole have got physical appearance. This vacancy of electron in the negative energy state, that have got physical appearance. So this will manifest itself as positive charge. Okay, so positive charge, we call it as positron. Okay, this is the symbol for positron. Charge is equal to positive, mass is equal to plus me, positive mass, so it will have positive kinetic energy. Vacancy in the negative energy state manifests itself as a positive charge, positive mass, positive kinetic energy. It has physical appearance. We call it as positron. Where is the vacancy? In the negative state only, but it has got physical appearance. That is a particle. We call that as positron. So quickly, any logical question, okay? We shall first deal with mathematics later at the end of the quantum mechanics. Then again, I'll explain this one.
So the momentum.
Again, that's very good question. If negative, these particles are not visible, isn't it? Where do you apply this gamma ray? No, it happens actually. Gamma photon, okay, nearby the nucleus. Okay, I'll tell you why it should happen nearby the nucleus. Okay, so gamma photon nearby the nucleus splits into two particles. Now, in this process, gamma photon is absorbed, isn't it? It disappeared. What are the product? One is electron, one is positron. Is that okay? So we say gamma photon so splits into electron and positron. Is that okay? Gamma photon will split into electron and positron. This is found later after 4 years. So Dirac gave the theory in 1928. I think in 1932, somebody found in lab this pair production. He expected this pair production 4 years before it is found in lab. So neutrons and proton, they also follow the same theory because they are also Dirac particle, I mean spin-half particle. They also follow the same theory, but not bosons, okay? For bosons, so there is a different theory for that one, okay? Now look at here, this event, splitting of... Yes, so tell me.
How isolated electrons exist?
How isolated electron? No, again, if any atomic electron is there, look at here, that is not because of this event, okay? That is not because of this event. Again, wait a second. So let me explain like this. If this happens, look at here, this positron and electron will not last for a long time. It will again annihilate. We call this one pair production, am I right? Pair annihilation. This has very less lifetime actually. Are you getting my point? It will quickly annihilate and again this will be completely filled always. Are you getting my point? So this will happen for very short time actually. You just check out how long electron and positron exist actually. Is that okay? So that's why there is no problem with our positive energy electrons in the universe, okay? So whatever the pair production that happens, pair annihilation happens quickly actually. So that these are completely filled only. Are you getting my point?
But in pair annihilation, the two gamma photons are...
No. Again, that needs some conservation law. So let me talk about that one. Okay. So we shall discuss that one in particle physics. So these are all comes under particle physics only.
In case of quantum effect, you have said that we will collide photon with electrons.
Yes.
And then the photon gets scattered. Now, the electron should be free.
Yes.
And the energy region is X-ray. The gamma ray is needed to pair production.
Yeah, in the gamma ray actually, pair production dominates it.
How can the electron be free for Compton effect?
No. Compton effect, I said electron is free by comparing incident X-ray photon energy, which is of the order of kilo electron volt. If electron is there in the atom, if it has energy, bound energy, free energy, it is very less actually. It's of the order of electron volt. We are talking about kilo electron volt. So again, with respect to that kilo electron volt energy, you can neglect that one. Even if you take care of that one, again in the calculation, at the end it will not stand. You can neglect that part. Are you getting my point? Now, why are you saying that about rest electron or something? So again, it is not related to this one, isn't it? Quickly. Now look at here, pair production will not happen in a free space. If it happens in a free space, look at here. So let me tell you like this, okay? Suppose an electron from here, it goes here, okay? So that when it goes here, very, very near to this one, it is almost at rest, isn't it? And when positron is here, this is also almost at rest. Look at here. So there is one gamma photon whose h nu is exactly equal to 2 m0 c square, okay? If it splits into so electron and positron. If this splits into electron and positron, look at here, those will not have any kinetic energy. So those will be here and here, isn't it? Those will not have any kinetic energy. So any particle which is here above this level, it will have kinetic energy. This part is kinetic energy. This part is rest mass. If suppose one electron is here, This part is rest mass energy. This part is kinetic energy. Is that okay? We have to subtract rest mass energy to get kinetic energy. This is the total energy equation. You have to subtract by minus m naught c square to get kinetic energy. Is that okay? So now look at here. If a gamma photon of energy 2 m naught c square, if this splits into electron and positron, then those electron and positron should be at rest, isn't it? Now look at here. This gamma photon will have some momentum. P is equal to h nu by c. Very high, what you call, momentum, isn't it? So now it splits into two particles. Final products have no momentum. Momentum conservation is not followed. That's why this event can happen only nearby the nucleus. I'll explain this one again in particle physics. Okay? To conserve linear momentum, there should exist a what you call big mass or something nearby that one. Again, so to assist this process, are you getting my point? So that's why this process will not happen in vacuum. Pair production will not happen in free space. It happens nearby the nucleus. So that's again observed in 1932. Predicted 4 years before.
Sir, once the hole is created in negative energy state, then it is possible for the electron to come from positive energy state to negative energy state.
No, this electron itself come back actually. Are you getting my point? Again, these two itself, what you call this E plus E minus itself go to gamma plus gamma. So 2 gamma photon will be produced, isn't it? If I am not wrong, 2 gamma photon will be produced. This has very less lifetime. Now your question is very good. When this happens, why other electrons quickly go to this state, isn't it?
Like PN junction.
Like in case of PN junction, that would happen, isn't it? Hole will be filled by other electrons. Yeah, very nice. But it has very less lifetime. Just check that out. Very less lifetime. It will annihilate again. Okay. I don't know much about antiparticle of neutron. Okay, because neutron is not a fundamental particle. Okay, it has composition inside that one. So you better to deal with the fundamental. The electron, you can't. It doesn't have any more composites. Okay, electron is elementary, very elementary. Okay, so but neutron, proton, those have what you call. But all elementary particle again have got what you call antiparticle. Some elementary particle are antiparticle itself. Okay, some bosonic particle. We shall study them. Okay, anyway, it's a particle physics concept.
So what is meant by here the free space? I mean, what does it, you said that H is equal to 2 m naught c square. Those
If no, suppose if this have again, if photon is moving in free space. If suppose suddenly 2 electron, so electron and positrons are created. Okay, which are at rest according to that graph. I hope you can get to know from electron from here it goes here. Okay, so then look at here. Before you have some momentum, after the reaction you don't have any what you call p value, isn't it? It will not conserve momentum. That's why there should be some nucleus which should take away some part of the momentum actually to conserve momentum actually. Is that okay? So that's why pair production can happen only in the assistance of some big particle. Nucleus usually nearby the nucleus. Okay, anyway, we shall study this one. Okay, you hold on this one because now I have to think on particle nature of light this way. Okay, again we have to direct our thinking towards that one. Okay, we should not divert here. It's not particle physics, but I hope you should know that. Look at here. Now if x square is equal to 4, never ever write x equal to 2. What is x equal to? Plus or minus 2. Is that okay? Yeah. So each and every mathematical expression have got some physical meaning. Is that okay? Some mathematical expressions we might not have found physical meaning yet. Is that okay? Which may find. Okay. Is it necessary to have physical interaction between electron and positron for pair annihilation? No. Again, single electron cannot give two Again, look at here. Nature follows conservation law. This comes in particle physics. Okay, charge should be conserved. One electron can two electron cannot give what you call annihilate or something. Are you getting my point? If pair annihilation happens, you should know that. Look at here. Electron from here, it is filling out this hole by emitting photon of energy greater than 2m0 c square. Is that okay? So again, nature follows some conservation law. Okay, there are no interaction found which violates those conservation law. Conservation of momentum, conservation of energy, relativistic energy. So conservation of charge, lepton number, baryon number, we are going to study in the particle physics. Okay, just hold on that thinking. Okay, we shall spend sufficient time on particle physics. Okay, I have studied that one. I mean, again, even though we don't know the theory behind particle physics, but I'll try to make it more and more comfortable. Okay, more and more comfortable. Okay, yes. So now this is the whole thing about pair production, but it also talks about particle nature. Okay, we have studied that one. How pair production talks about particle nature, because this is also kind of instantaneous process, isn't it? How do you talk about photon? What you call? Are you getting my point? Again, I introduced this one because this is also an experiment that proves particle nature, isn't it? How it proves particle nature? I forgot. Anyone?
Nature says that the energy supplied has to be continuous.
Energy, if
The discreteness of the photons make it possible for pair production.
yeah, a kind of sudden disappear and I mean instantaneous process, isn't it? That's also happens in case of photoelectric effect, which is instantaneous process, isn't it? That instantaneous process, because that it is instantaneous process, it can't be explained by wave theory. Wave theory says energy is received continuously, isn't it? It's a kind of sudden event. That's also one thing. But anyhow, again, just read out Jatila. I think you may find much more idea. Okay. Pair production 1.2.4. Okay. We shall put a hold on this one. We shall discuss later. Is energy of massless photon. Is energy of massless. And I'm not getting that one. Can you see the comments? You have mobile? Okay, yeah. Yeah, it's a kind of, again, you can see again in the wave perspective, I think you can't, again, why we can't explain pair production using wave theory? Just like very similar to that earlier question that I asked, okay? Try to develop that one. So that's a good idea. Is that okay?
So what is the meaning of negative energy there?
What is?
Meaning of negative energy?
No, negative energy means, look at here, what is the meaning of ground state, first excited state of hydrogen atom? It has exact meaning. Are you getting a point? You say ground state of hydrogen atom in minus 13.6 electron volt, isn't it? So next state minus 13.6 by, similar to that one, state can exist, okay, with energy. Particle can be in that state with energy, possessing energy, that is negative. But it has no physical appearance if particle is there in the negative energy state.
So is it possible the photon should be greater than 2m0 c square?
Yes. I mean, if it is less than 2m0 c square, no pair production will be produced. Are you getting it? For electron, suppose if you take this is Me, okay? If you take Me for electron, if you are discussing about electrons, okay? If gamma photon of energy less than 2 Me c square will never produce pair production. That's also kind of boosting for this theory, isn't it? Are you getting my point? That's also very important. So these are the questions, small questions that may be designed, okay? What is the minimum energy required for pair production? If rest mass is m0, like that. Is that okay?
Sir, whose equation under root is p square plus m0 square cube और कोई रिलेशन नहीं है डायग्राम का आपने पढ़ा है डायग्राम में वाली
Yeah, this equation I have drawn in diagram. Is that okay? Because you can't mute this part. This is rest mass energy part. Is that okay? That I have drawn there. So that's why this forbidden gap appear. There are no states here. Particle can never have any energy in. So again, between these. Are you getting my point? That's what I'm saying. So that's why first I argued. If you see positive energy state, that should be greater than this one. This again, root of this one. If you have negative energy state, that should be less than this one because added, isn't it? Something is added to that one.
I have a doubt.
Yes.
I mean, so you said that
Yes.
the particle electrons in the negative energy state jump from spontaneously jump to positive energy state, have a physical appearance, and
No, not. Don't say spontaneous. Don't say spontaneous. By absorbing photon. Yes, continue.
Yeah, okay, by absorbing.
Yes.
And the holes created or the vacancies created manifest themselves as positons, right?
Yes.
So what you are saying is, for a very small instant amount of time, an atom's electron would be like increase or decrease.
For very small instant of time. Speak out again.
For a very small amount of time, and like an atom's number of electrons would increase or decrease.
In the
This
universe.
is happening, right?
In the universe. In the universe, that's what you're saying.
But we are annihilation.
Number of electron increases. That's what you're saying, isn't it?
Yeah. For a very small amount of time. Even though that may result in the annihilation of the pair that has been produced back to the gamma photon, but still, for a small instant of time, you were saying that the number of electrons might increase because apparently that is what happens. Is that so the case?
No. Again, why not? Why not? Isn't it? Again, for small instant of time. Yeah, one more electron is produced in the nature. Why not? It can happen. Is that violates any particle physics law? No, nothing is violated. Okay, because this conserves charge, isn't it? Again, one more negative charge is produced, but you have one more positive charge also, isn't it? Which is produced along with that one.
Yeah, it's okay.
I don't think it will even violate. Suppose if you take total universe have got zero charge. No, that kind of concepts are there in particle physics. Then it will not violate. Okay, I think it's okay. There is nothing violated actually. Yeah. Anyway, we shall deal little more about this one. Okay, in particle physics because particle kinematics questions are there in exams. Yes.
Sir,
Yes. Speak out. Speak out.
engineering is much higher then the pair production can
Speak out again. I didn't.
production can take place.
Again, speak out again. I didn't heard first part.
Sir, if h nu is much higher, then the pair production can take place.
Yeah. Again, if h nu is greater than 2 m naught c square, it's of the order of gamma photon. That means mega electron volt. Again, in case of electron positron production, it should be greater than 1.02 something mega electron volt. Okay. 0.5 mega electron volt is electron rest mass energy. Am I right? Double of that one. If it is little more higher than 2 m naught c square, then also pair production happens. Extra energy will appear as kinetic energy of the products. Is that okay? Again, this is also probabilistic event. Okay, it's not happens. What you call? You need to wait for that one. I mean, are you getting the point? You can't make it to happen. You have to wait for this one. These are the probabilistic event that I think you can see in RD1. So if I read that one, I'll try to explain. Okay, if photon were wave, then how it can break into electron positron? That's true. If it is wave, how it can break into? But I need much more, right? Anyway, we shall hold on that one. What's the time? Now look at here. This all talks about particle aspect of radiation, okay? This all talk about, again, wait a second, I'll try to answer one more thing. Somebody asked the question in the morning, in case of Compton effect. Compton effect is a electromagnetic interaction, am I right? Now look at here, that electromagnetic interaction, whatever we say in particle physics, that has a different mechanism, okay? That field theory interaction have a different mechanism than whatever the interaction that whatever we study in the theory which is before field theory. Mechanism is different. Even though it is said like that electromagnetic interaction, okay, mechanism is different. I better to say like that, mechanism. I couldn't get that word. Is that okay? By exchanging particle like that. So that's why, again, even though it says again, why I said mechanism is different, because again it is not, you should not compare, you should not treat that electromagnetic interaction like electric field and magnetic interaction, whatever we study in classical electrodynamics, okay? Both are different. We are going to change the mechanism of the interaction itself, okay, in the field theory. So that's why, so again, so even though it is a electromagnetic interaction between two particles, photon and electron, they should not be thought of electric field and magnetic field of EM wave interacted with electron, okay? Because that mechanism, whatever we say in particle physics, that is different mechanism of interaction, new mechanism, which explains a lot of things, okay? Yeah, let us put a hold on this one. Again, later we shall discuss that one, okay? Now look at here.